This video, we're going to prove the following fact. Let the mapping tau of AB for all AB and R map the rails into the rails by this rule. Okay, that is tau of 7,3 on x. It will be 7 times x plus 3. The a gets multiplied by the x, and you add on b. That's all it does. But now they're giving us a subset of this mapping. G is the set of all tau sub AB only if a is not 0. Just for the record, if a was 0, you will get 0 times x plus b, which is just b. So, given this subset G, we want to show that G is a group under composition of mappings. So, for the proof, let tau of AB and tau of CB be elements of G. And of course, A and C are not 0. Okay. So now, what would the composition be? Tau of AB composed with tau of CD, say on X. Well, first you do this one. So tau or CD on whatever this result gives you. But that gives you ax plus b. Okay, whatever is in here gets multiplied by c, and then you add d to it. So we get c times what the argument is plus d. Well, this is acx, a multiple of x, plus bc plus d. BC plus D. But that's just tau of the multiple of x and the constant. It equals to that. Oh, and that's in G. But let's be careful. Let's be careful. This cannot be 0. AC cannot be 0. Well, sure. A is not 0. That's how it got to be in G. C is not 0. So note that AC is not 0. So yes, it is in G. We have closure. Okay, now if you take tau of AB, what can you multiply it by? What can you multiply it by? That is, what goes down here? So you just get back. Well, let's first, before we can talk about inverses, we need to talk about the identity. What can you compose this with to get back x? The answer is 1, 0. Because tau of that is going to be, well, tau 1, 0. Tau AB of that will be ax plus b. Well, what do I do to this? I multiply it by 1, so it won't change. And then I add 0, so it won't change. I get 1 times ax plus b plus 0. But that's ax plus b, also known as tau of AB. Okay, so this here is the identity element. Okay, which, by the way, tau of 1, 0, tau of 1, 0 on x will be 1 times x plus 0, which is x. So if we get back x, then we have inverses. What could you multiply or compose tau of AB by to get this back, or to get that back. Actually, let's do it on the other side. So I didn't put down what's there yet. Actually, let's do it the other way. I apologize. On X. So first we do tau on that, and then we'll do the next tau. That's going to be ax plus b. Now, we want to get back x. Well, if we multiplied by 1 over a, then we'll have x plus b over a. So we got back the x. We don't want b over a. So how about we do negative b over a? So what happened is, so let me put that over here, 1 over a, negative b over a. So first, you multiply this by the argument, so you get 1 over a times ax plus b, and then you take away b over a. And this definitely works out, because this product is just x, plus 1 over a times b is b over a, but then we take away b over a, so we get x. Ah, that's the inverse. That's the inverse. So, inverses are in G. And we also showed that G was closed. We showed it right there. So we have closure, we have inverses, therefore G is a subgroup. G is a, does it say group? Yeah, G is a group. G is a group. Now, okay, let me say this. Statement 1. Associative law holds in composition of mappings. Okay, and we found, so the ID element is tau of 1, 0. So we found we have associative, we have closure. Let's do it in order. We have closure, we have the associative law, we have the ID element, and we have inverses. We're a group. Can only use the rule that I was about to use if we're talking about subgroups. If you like watching videos like this, please subscribe to my channel, leave a comment, click the like button, do all the nice things. Tell your friends and families and enemies about my channel. Don't forget, watch and learn. See you folks in the next video.